Okay, welcome back, everyone. Her name is Dahlia, the Dalmatian. I've been getting a lot of questions about problem 1 on the homework, so I wanted to talk about that one and maybe some other things. And by the way, you can't answer every, well, you can, but given what we've done in class, you should not be able to answer 3D as in David at this point, and maybe, I don't know, maybe 6 or 7. So we're gonna cover the rest of the material today. Okay, so in problem 1, we've got some, this is on homework 2, we've got some Bernoulli random variables. They are 0s and 1s. And the question is it a Markov chain? And if not, prove that it's not. And I put rigorously in there, which scared some people, but I just didn't want people saying, oh, it's not a Markov chain because the next value depends on the last 2 values, because I don't think that's quite enough. We had our good defective Markov chain where we kind of lumped 2 values into 1, except that's not happening here. So I just wanted a little more explanation. And so we have the x1, x2, ... These guys are independent and identically distributed. I don't think I've used this really common stats notation in here, but squiggly line have the distribution Bernoulli with parameter p, and then we usually put an IID over that to stand for independent and identically distributed. Independent and identically distributed also is a random sample. Okay, so we defined yn to be xn plus xn minus 1. And this only makes sense for n greater than or equal to 2. So is this a Markov chain? What if we worked out a probability? Let's see, I'm going to need at least 2 steps to prove it's not a Markov chain, because how could you prove it's not a Markov chain? If you were trying to, you could look at any 2 time steps, and this one starts at time 2. So let me look at like y4 equaling some value, given y3 equaling some value, and y2 equaling some value. If we pick something, I don't know, something like, let's just consider this, 0, 1, and 0. So check this out. Because y2 is 0, y2 is x2 plus x1, and the x's are 0s and 1s. There's no negatives. So this tells me that x1 and x2 are 0. And so I could take that over here, because y3 is x3 plus x2 is 1. And because I know that x2 is 0, then I know from this combined with this that x3 must be 1. So given that, can you find the probability that y4 being x4 plus x3 is 0? And I'm not going to write anymore because I do want you to pull it all together for your homework, but there are no negatives, and we already know that x3 is 1. So I think we can't get y4 in this case to be 0, which is fine. It's not undefined. The whole probability is 0 for this particular example of these 3 points. And so if you redo this probability and you maybe change this, if you get something different, then it can't be a Markov chain, because the thing in the box is supposed to equal this. And yet if I made another box with a different y2, it's still supposed to equal that orange circle. So if I get 2 different probabilities, that would be a way to show that the sort of y4 given y3 probability is not enough to determine probability without further history. And I think there's some poor choices for what you might consider changing y2 to. If you change it to like y2 equals 1, then that doesn't lock in the x's for you. That tells you that either x1 would be 1 or x2 would be 1, but not which one. So maybe change it to something else. And so my point is that if you compute this probability with these two given things, and then you compute it again with this being identical and this something else, if it's not the same, it can't be Markov because they're both supposed to be the thing in the orange circle. Now, I'm not saying it's not Markov, but I pretty much said it's not Markov, I guess. Problem 2 is totally a good defective problem. It's an overlap. And so in problem 2, we've got a Zn defined to be xn minus 1, xn. And so if Zn, which takes on the value 0, 0, 0, 1, blah, 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 if Zn is going from 0, 0 to 0, 0, this really corresponds to like 3 time steps. So I'll call the middle one n and the right one n plus 1, and then n minus 1 over there. So 0, 0 means I have 2 zeros in a row, and then I have 2 zeros in a row. And so you definitely need them to match in the center. So if you recall in the good and defective chain where we brought 2 states into the Markov history, you can't, for example, so the probability of going from say 0, 0 to 1, 0, that's not happening because you do need these states to overlap and be the same. But the rest of it, it's the good defective problem. Okay, 3 should be fairly straightforward. 3D, D as in David, we don't know what that means yet. We're going to learn that today. 4A, I'm not going to say anything about it, but it's a trick. So at the end last time, we were talking about recurrent and transient states. And a recurrent state is one that you will return to with probability 1. So you may never hit it. You may have some kind of matrix where you start the chain and you never can hit state I. But if you start at I, the fact that you will come back makes I recurrent. So I can be recurrent even if you can never get there. It's all about once you're there, what will happen. And then the opposite of recurrence is transience. So we talked last time about a recurrent state you will return infinitely often because this is, I don't know if I'm going the right way or I'm mirrored, but this is a state space and this is time. And starting at some state I, if it's recurrent, you will return. And then the Markov property says you're starting over and you will return again. For a transient state, you will eventually escape, never to return again. And that's where we were. We were trying to find, or we postulated, or we said that we wanted to find the expected number of returns to a transient state. So that's what we're going to do. I'm going to let I be a transient state. And given that we start at I want to know the expected number of returns. So just as a quick reminder, how we define transience and recurrence, we talked about a first hitting time. So we let Ti be the minimum time at times greater than or equal to 0 for us to land in state I. So then we define the probability. We're using this notation Gi, and we're defining this to be the probability that Ti is finite given that we start at state I. So by the way I define T with that yellow one, just because we're starting there doesn't mean we're hitting it yet because we're only counting returns. And so if Gi is 1, this is the definition of I being a recurrent state. And if Gi is less than 1, it is the definition of being a transient state. Okay, so again, I want to know the expected number of returns to a transient state. So starting with this, I'm going to let n be the number of returns to state I. And implicit in me writing returns, this is at times 1 or greater, not times 0. So at times 1, 2, 3, And because it's returns, we're going to condition everything on starting at state I. So I want, for a transient state, the expected value of the number of returns given that we're starting at state I. Maybe my n should have some dependence on I, but I'm just going to stick with this. So n is the number of returns to state I given that we've started at state I. So this is what we're trying to figure out, and we can actually figure something more out than this. We can find the distribution of this conditional random variable. So, and if we know that distribution, then we can also find the expected value or mean. So even better, if I look at n given x0 equals I, has what distribution? So the squiggly line says has the distribution. You know, is it a normal distribution? No, that's continuous, but let's see what it is. So it takes integer values from, we could never return, so n equals 0 is a possibility. Okay, thank you. That's what was hanging me up there. So check this out, a couple of bullets for you. And by the way, to remind you of our new notation, we can also write this as the expected value of n, and then put an I down here as a subscript on the expected value. That means that we're starting at I. Okay, so the first thing I want to look at is the probability starting from I that the number of returns is greater than or equal to 1, which, just for the record, this is the probability the number of returns is greater than or equal to 1, given that we started at I. So I have computed nothing there. Those are two notations for the same thing. And so this means we're going to return at least once. This is probability return to I at least once, given that we're starting from I. And that's really our G sub I. So our G sub I is the probability that we will return in finite time. It says nothing about exactly once or twice. This is the probability you return at least once. And so this guy is G sub I. Okay, so the probability I return at least twice, this is the probability starting from I, we return at least twice. So we're going to use the Markov property, and we're going to say, what's the probability we return at least once? And now we're starting over, and we want to say, what is the probability we return at least once? So by the Markov property, this is GI squared. So return once, then start over to return once more, and it's an intersection. So we're returning at least once, and now starting from there, returning at least once. So I'm multiplying the two probabilities, and I'm using the independent kind of increments of the Markov chain. Okay, I think you probably get the pattern, but I'm going to write just one more. The probability we return at least 3 times is going to be the probability to return. And once we return, we can ask the question all over again, because now we're starting at I. And we're going to get GI cubed, multiplying those independent excursions. You know, the values of a Markov chain are not independent of each other, but the trip from I to I is independent of the next trip from I to I. Okay, I don't really want to know greater than or equal to probabilities. So let's try to figure out the actual equal probabilities. And get another color. Okay, so now I know the probability starting from I that the number of returns is, say, 0. This is 1 minus the probability starting from I that the number of returns is greater than or equal to 1. And that was G sub I, so this is 1 minus G sub I. I also know the probability starting from I that n is 1 is, I really don't know what to do about this lag. I've tried so many things. It is the probability starting from I that n is greater than or equal to 1. That's a lot of things happening. We want the exactly equals 1, so we're going to take away the greater than or equal to 2. So we just focus in on n being 1. So the first one is saying, what is the probability n is 1, 2, 3, 4, 5, 6, 7. And the second one is, what is the probability n is 2, 3, 4, 5. We're taking that out, so we just get 1. And so this is gi minus gi squared, which I want to write. I want to factor out this gi because I think it will be illuminating. Okay, so the next one is going to be exactly the same. The probability that n is 2 starting from I is going to be the probability starting from I that n is greater than or equal to 2 minus the probability starting from I that n is greater than or equal to 3. And this is gi squared minus gi cubed. And this is gi squared, 1 minus gi. And so we can easily write this down, the probability that n equals k, because I think we've caught on to the pattern. So I want to remind some of you about the distribution that others of you are already seeing, and that is the geometric distribution. So just as an aside, we say that x has a geometric distribution with parameter p if this actually means one of two things. And if you've had a class with me before, you'll recall that I put a subscript on geom. I put a 0 or a 1, but that's totally not standard notation, so I'm trying to stay away from it. The geometric distribution comes up when you have a series of trials and you have success or failure on any one trial. The trials are independent, and the probability of success on any one trial is a little p and failure 1 minus p. And x counts either the number of trials until the first success, in which case it's a random variable that starts from 1, or the number of failures before the first success, in which case it's a random variable that could start at 0 because you could get success right off the bat. So I think we're going to need the one that starts from 0 to kind of match ours. The probability that x is 0 is this doesn't make sense in the problem because I didn't write all this stuff down, but it's the probability of getting a success right off the bat, which is p for the geometric. I think hopefully everyone has seen this, but you can go back into that chapter 1 in the notes that never finished, because I am putting notes in the modules, but I haven't finished that. I haven't put them into the book. But the chapter 1 tells you about all of these distributions. The probability that x is 1 is the probability of a success and then a failure. Oh, sorry, the other way around. A failure, then a success. So this is 1 minus p times p. And it's pretty easy to come together and figure out that the probability that x equals x for this geometric is going to be 1 minus p to the x minus, to the x times p for x equals 0, 1, 2, on up. This is one of the two geometric distributions. And so I don't want to do the mean of this, but you could look up the mean of the geometric or recall it, the expected value of this x. Yeah, the expected value of this geometric is 1 minus p over p. If you're looking at the other geometric that starts from 1, it's 1 over p. And now let's do what Sage just asked. Let's figure out what we have. For in our case, I'll go back to yellow. We've got the probability starting from I that n is equal to k. This is gi to the k times 1 minus gi. So remember, I do have this conditional the conditional that I'm starting at state I. So this tells me that the distribution of n, given that I started at state I, is geometric, and p here is in the kind of opposite place. Like this is my gi, and this is my 1 minus gi. So the p is 1 minus gi, which is the probability of escape. Yes, never to return again. So geometric distribution is really something people should know. Shoot me an email and we can get together and talk about it if you need more refreshing on that. Oh, so now I also know the mean. The expected value of n starting from I, and then this is pure notation. I'm not, you know, there's no, why is this true? The expected value of n starting from I is supposed to be 1 minus p over p, but our p is 1 minus gi, so this is gi over 1 minus gi. This is the expected number of returns to a transient state given that you start at the transient state. And for transient states, this gi is less than 1, and it's a probability. So we do know that this is finite if I is transient, since that means that gi is less than 1. And although everything we did kind of relied on it being transient, this formula kind of works for a recurrent state as well. I mean, yeah, if gi is equal to 1, then it's undefined. But if you think of it as approaching 1, we're getting 1 minus something that's getting closer and closer to 1, this thing blows up when gi approaches 1. So it's saying the expected number of returns to a recurrent state is infinite. And yeah, and so I was saying that also makes sense for recurrence, because if gi is 1, yeah, it's undefined, but if you think of it as approaching, it's kind of blowing up as the denominator goes to 0. Okay, I promised you that I would show you that recurrence and transience are class properties. That is, if I and j communicate, then they're either both recurrent or both transient. And to that end, I have one theorem to fit in, which I think is going to be really helpful. And I think it's going to be helpful to you a lot of the time for trying to show whether something is recurrent or transient. So here it is, the theorem. So suppose that, no, not suppose, I'm going to just state it. State I, just waiting for my handwriting to catch up. State I is recurrent if and only if the sum as n goes from 1 to infinity of p sub I, like super n, so no, it's not there yet, but this is the probability you go from I to I in n steps. If this is infinite, that sum does not have a nice interpretation, because first of all, it's a sum, and usually we sum probabilities when we have disjoint things. And yet, if I go from state I back to state I in 5 steps, that doesn't mean that I didn't already go back in 4 steps, because it's not about first returns. So the event that I go from I to I in 5 steps actually may overlap the event that I go from I to I in 3 steps, and then I happen to go back to I, or maybe I never left I. So this is not a sum of a bunch of disjoint probability things. It doesn't really have an interpretation, in my opinion, but I should say, I think it's an if and only if, but I'll say equivalently, I is transient if and only if the sum is finite. I know it's not there yet, but this is a really useful criterion for determining recurrence or transience in chains where it's not obvious. And I think remembering which is which makes sense. Well, it does to me, although these sums of these probabilities don't really have an interpretation as anything specific happening. You would think that if the probabilities are larger, then the sum would diverge to infinity. And they're going to be larger if we have more of a chance to return. So that's what helps me always connect infinity to the recurrent case. Like probability of returning is non-trivial, and these numbers are going to add up to infinity. Whereas in the transient case, the probability, I'm circling the one below, in the transient case, the probabilities are kind of small and eventually 0. And that's how this sum converges. Okay, so we're going to use this to show that recurrence and transience is a class property, but first let's prove this. And we just need to show one case. The other one is automatically true. So I think it's easier to show the transient case. and we're going to use what we just did. So a state I is transient if and only if G sub I, the probability we will return, is less than 1. And this happens if and only if the ratio we computed, Gi over 1 minus Gi, is finite. And that fraction is the expected number of returns given that we started at state I. So I probably should define my notation here, but I'm not. That n is the same thing it was before. We're letting it be the expected number of returns. Okay, so given that, I have infinity greater than the expected value of n, given x0 is I, and n is counting a number of returns. And so I'm going to count that by looking at each and every x in the chain and checking off, did I return or did I not return? So I'm going to write this as a sum of indicators. I'm going to write this as the sum as little n goes from 1 to infinity of, so this is a capital I sub, if you haven't had a class with me, you probably haven't done a lot of indicators. And if you have, this is usually not the way I write them. So let me write it and then define it. So this indicator function. It's got a capital Xi in here. So it is a random variable. And it's going to be 1 if Xi equals n, and 0 if Xi does not equal n. So if I want to count the total number of returns, not n, not what I want. I want I. In my indicator back here, the subscript should be x sub n, and the state we're visiting should be I. I wrote x sub I equals n, should be x sub n equals I. So again, every time you hit I, you score a 1. So you're adding them up. And then expectation is a nice linear operator. I do want to get through some other things today, so I'm kind of rushing this point. In this class, you don't need to justify this for me, but you should be thinking about it out in the real world. Expectation is a sum or integral. And so right now, by pulling the sum out, I am interchanging an order of, in this case, summation. And if everything is finite, that's absolutely fine. But for infinite sums, it could go wrong and not converge. It's not going to happen to you in this course, and it's really a result of something called the bounded convergence theorem that I don't want you to have to know or quote. Probabilities are just nice. They're compact and bounded, and they're things between 0 and 1, and this expectation of a really finite discrete random variable. I don't want you to think about it unless you're already thinking about it. Then I want to make you feel good about it. So I interchange the sum. And then we've done the expected value of an indicator before. It is the probability of the event being indicated. Yeah, sigma algebra vibes for sure. Oh, you told everyone the trick. The expected value of xn equals I, given x0 is I. This is 0 times the probability. The indicator is 0, given x0 is I, plus 1 times the probability. The indicator, that xn is I, given x0 is I. And so this is just the probability that the indicator, so it's 0 times the probability this indicator is 0, plus 1 times the probability this indicator is 1. Those needed to be in there. So this is the probability that the indicator that x sub n is I is 1, given that x0 is I, and that indicator is 1 if and only if xn is I. So this is the probability that xn is I, given x0 is I. This isn't the first time we've done this in this class, maybe the second, but I just want you to get it down that the expected value of an indicator is always the probability of the event being indicated. In this case, the event being indicated is that xn is I. So we get the probability that xn equals I, and yet everything lives in conditional land. Okay, so going back up to where I left off with my sum of expectations, this is a sum as n goes from 1 to infinity of the probability that xn is I given x0 is I. And if you could see it in front of you, you would say, hey, what I see is me going from I to I in n steps. So this is the sum as n goes from 1 to infinity of the probability we go from I to I in n steps. Not for the first time necessarily, just in n steps. How do we go from I to I? And so this is finite. We've got this sum is finite. I'm circling way up to the upper left. And this is now a way we can establish transients. Oh yeah, I thought I was proving the next thing. So we have shown that I is transient. I'm circling up. We have shown that I is transient if and only if, these were all if and only ifs, if and only if that sum at the very end is finite, which is what we wanted to show. Okay, so I can finally show you that recurrence and transients are class properties. I usually don't even call this a theorem, just kind of a fact, but I guess it's worthy of being a theorem. So recurrence and transients are class properties. And by this, I mean that if I and J are in the same communication class, if they communicate, then they're either both recurrent or both transient. That you can't have a communication class with some recurrent and transient states in it. So these are class properties. And this means, i.e., if I communicates with J, then either both are recurrent or both are transient. This question came up last time and I had a really poor explanation like, well, you leave the set and then you can't come back, but here, let's prove it. Okay, so to prove this, let's pick a case. It is if and only if, right? Because if we prove this for recurrence, like if I is recurrent and I communicates with J, if we prove that J is recurrent, then we've proven it the other way around. Because if we start with I transient and we, by contradiction, try to assume that it goes to a recurrent state, J, then J communicating with I says, no, I had to be recurrent. So we just need to prove one case. And let's do the recurrent case. So we are done if we can show our new criterion. Done if we can show that the sum as n goes from 1 to infinity of PII super n is infinite. And what do we know? So we're starting with the recurrent case. So I probably should have said, let I be a recurrent state. So I'm saying it now, but not writing it. So I know that the sum as n goes from 1 to infinity of PIIN is infinite. Now I feel really guilty. So up here, I'm going to say, let I be a recurrent state. That's what gives us this result from the previous theorem. Because it's recurrent, we know that sum is infinite, that we go from j to j in n units of time. When we sum those up, we get infinity. Thank you. Oh, it can be, because remember our communication classes we wrote down last time. We had, like, this is just an example of a communication class. We made a bracketed set where we said you can go from 1 to 3 and you can go from 3 to 1. They communicate, you can go back and forth. But it may be possible that you could go from 3 to another state 4, in which case you're stuck outside. one, I'm just going to make word states just so I can finish this off without adding more stuff to it. Maybe you can go from 1 to 3, 1 to 1, 1 to 3, 1 to 4, and then from 3, you can only go to 1. I don't know. So in this case, 1 and 3 communicate because I can get from 1 to 3 and I can get from 3 to 1. But starting at state 1, there's a chance I go out to 4 and then I'm stuck there and can't come back. So 1 and 3 do communicate, but they are transient. The other thing I already know here, given that I'm assuming that I is recurrent, that's not true. I already used that piece of information. Given that I'm assuming that I and J communicate, so I communicates with J implies there exists a couple of interesting integers. There exist integers n and m greater than or equal to 0, such that the probability I go from I to j in n units of time is greater than 0, and the probability I go from j to I in m units of time is greater than 0. That's actually one of the delays has been in me posting my videos. I do try to play with time and make this catch up in my editing. Okay, so I have 1 minute. Okay, I want to show that the sum going from j to j in n units of time is infinite. So let's look at the probability I go from j to j in, say, k. You know what? I am rushing, and I don't want to use n here because I want to save n for my sum. So I'm going to change that to like a k. Okay, so this isn't going to make any sense because it's going really fast, but for some of you, for the completeness, I'll do it, and then I'm going to have to start here next time. The probability I go from j to j in k plus n plus m units of time, this is greater than or equal to going from j to I in m units of time, and then going from I to I in n units of time, and then going from I to j in k units of time. This is Chapman-Kolmogorov, where we pulled out one term. This is going way too fast. So what I want to do now, I'll do it next time, is I'm going to sum both sides over n. And I'm going to use the fact that I know that this summed over n is infinite. And so this summed over n is greater than that. So it's also going to be infinite. And then I'm just going to clean it up by saying, by summing this as n goes from 1 to infinity, we're not really looking at the whole series. We're looking at summing the tail of a series. But if that's infinite, the sum of the whole series is infinite. And we will have proven that I is recurrent. So I'm out of time. That problem 3D, I haven't defined aperiodic yet, but I don't want to remove the problem. Sometimes I do if I don't get there yet, because it's going to be a 10-second answer once you know what it is. So I don't think it's going to be a big deal. So thank you. And